Hello everyone, welcome back to the channel. My name is Danny and today we're going to talk about threads in Rust. Basically, we're going to describe how to implement our code so that we can use multiple threads to run concurrently, not parallel, but concurrently, so that we can optimize it for the most speed and the most efficiency. So without any further ado, let's get right into it. Alright guys, so as you can see, I already started this project with all of the use, all of the import, everything's prepared. That way we're not wasting time. So let's start with a variable called data, and that's going to be a vector, right? And it's just going to be I32, just random numbers, it doesn't matter. Let's say 9. Okay, so we have a data vector of I32 integers, and then now what I want to do is start a new thread. So we're going to use thread spawn, and it's going to take in a closure, right? And the closure is not going to take any arguments. If there was arguments, it would be between these two bars right here, but typically there's no arguments. And then we're going to start the closure here, and all we're going to do is inside of this closure we just want to print out the data. So reading data from in thread, and it's going to be we'll make sure to use the debug implementation because vector does not have the print, the formatting implementation, so the regular print won't work. And there it is. Alright, so as you can see right away we have an error, and let's see what the error is. It says that we need to force the closure to take ownership of data, and the reason for this is because for threads, the compiler cannot guarantee which one will run first. It doesn't know if this thread will run first or the main function will run first. If the main function happens to run first, and then once the data gets dropped because the main function exits, this thread will now be trying to access a data that's not there. So the compiler cannot guarantee the race condition. It cannot guarantee that this data will always be there whenever the thread needs it. So in order for it to be able to continue, it needs you to move the data inside of the closure. So anything that's being used, any variable, any outside variable that's being used inside this closure needs to be moved into the closure, into the thread, pretty much. So we're going to do that with one simple word, move. And that move is going to move the data into the closure. So now we have a different problem, which is because the data has been moved in here, if we try to print it here, let's say reading data from main, right? And if we try to read the data variable in here, it won't allow us because the data has already been moved. I mean, this is pretty simple, straightforward stuff. Borrow of move value, it's already been moved inside of the thread, inside of the closure, so it cannot be used here. So as you can see right away, that's going to be the first problem, and we're going to solve that problem with a data structure called ARC. ARC stands for atomic reference count. So a reference count, all ARC does is basically wrap your data structure inside of a pointer. That's all it is. And ARC is able to be moved between threads. RC, for example, is a different data structure that does the same thing. However, it cannot be moved between threads. And ARC can clone itself so that we can have multiple pointers to the same data structure. And all it's going to do is increase the strong count. It's called a strong count of that data structure. So it won't be dropped. If, let's say, if one of the pointers go out of scope, it's not going to drop the data structure until the strong count goes down to 0. So let me explain, okay? Let me just go ahead and show you guys. It's going to be arc new, and we're going to wrap that data structure inside of the arc. So now it's going to return an arc of vector of I32, right? So what we're going to do now is, instead of moving the data inside of the thread, we're going to clone it first. So we're going to say let data clone equal arc clone, right? It's going to take in a reference of itself. So we're going to pass in a reference of data. So now data has been cloned into data clone. So basically, before we did this, data has a strong count of 1. But since after we clone it, now data has a strong count of 2. And all we did not do a deep copy, which is the entire data structure here. We did a shallow copy, just a pointer to the same data structure. So we're going to pass in that pointer instead. So reading data, and we're gonna run data clone instead of regular data. So now everything should be working fine. The compiler is happy, and let's try to run this code to see what it does. Right? Okay, so now it's working, but as you can see, it's not supposed to work like this all the time, and it's only by luck that it's actually working properly this time. If I run it again, I think because my computer is actually kind of slow, and therefore the main is actually not reading. I mean, it's reading slowly, so it allows the handle to actually run the thread before the main even exits. But what you're gonna see is eventually, it's gonna say reading data from main, and everything's gonna be read, and then there's gonna be times when there's only gonna be 1 or 2 items be read here, and it'll be the rest will be left blank. And that's the reason being is because, like I said, if the main goes out of scope, if the main function goes out of scope, everything gets dropped in here. Everything else there's no time for the thread to run. So in order for us to make sure that works correctly, is to make sure the handle gets joined with a join handle, and we need to unwrap that because it's going to return a result, and it's going to panic at runtime if it doesn't work. So now if we run this, it's going to make sure the thread gets ran first, as you can see. And the place where you put this join method matters a lot. If you put it after this print line here, what it's going to do is it's going to run the main function first up until here, and then this is where it'll stop and allows the thread to run. So join, basically what it does is it waits for the associated thread to finish. So if I leave the join up here, like I said earlier, what it's going to do, it's going to stop the code right here, run all of this, and then once it's done, then it'll go to the rest of the main function here. And that's why you see the threads being read first and then the main. However, if I go here and I place the join method here after the print function of the main function, we're gonna see something different. We're gonna see the main being read first and then the thread. So it's very important where you place the join handle as well. But let's just leave it here for now. Okay. All right. So that works fine. However, let's say if I wanted to mutate the data inside of the thread. Okay. How would I do that? So let's try to do that now. Let's say writing data, right? We're gonna write to the data, and let's do data clone dot push. Let's say we push a number 10. What is that going to do? Cannot borrow data in an arc as mutable. So arc is not able to mutate data, right? So that's just not its functionality. So what we need to do now is introduce a new concept, and this is called mutex. So mutex, the way I like to remember it is mutex basically means mutable, right? And it's actually mutually exclusive, meaning only one can use it at any given time. And we'll explain what that means. So what we're gonna do now is we're gonna wrap the vector inside of this mutex by saying mutex new. And we'll wrap that vector inside of the mutex, and then we'll wrap the arc around the mutex. So it's going to be multiple pointers happening at the same time here. So the mutex is going to allow us to basically, it's going to allow us to unlock and lock, and then we can mutate the values within that mutex at any given time. So let's explain what that means. So now the data clone is no longer the data itself, but now it's an arc mutex. So when we go in here, we're gonna say let data equal data clone dot lock, and that's gonna return a mutex guard. So what does lock means? Mutex only allow one thread to handle the value at any given time. So think of it like a baton. It just kind of passes baton around, and only one person that has the baton gets to manipulate the baton, gets to do whatever they want with that baton, gets mutated. So the lock, basically the mutex is gonna lock the data, right? And then once it's done doing what it needs to do, once it's done pushing, mutating it, once it go out of scope, once this mutex guard go out of scope, it automatically unlocks so that the next thread can repeat the process all over again. So at any given time, only one thread can lock up the value, mutate it, and then unlock it at the same time. So you can't have multiple things doing that at the same, that's going to create a race condition. So data clone, lock, unwrap. So we need to push it into data instead of data clone this time. Right, and data is going to be mutable, obviously. All right, so now basically that should work, and we should see that the data will now go from 12589 to 1258910. All right, let's see. Okay, and the reason why it's saying all this poison false is because we're reading from the data without unlocking it first. So let's go ahead and locking it first, I'm sorry, and then unwrap it so that we can get a prettier print at the end here. All right, so as you can see, we wrote into the data and we added a 10 to it. So now we're able to mutate the values of whatever it is that we pass into the threads. So now let's go ahead and add another abstraction to it. We're gonna go ahead and, what if we do multiple handles? Let's spawn multiple threads, save it inside of a vector of handles, and then we'll go through the handles later on, and for each one of those handle, we'll join it. So we'll allow it to finish whatever it needs to do within its threads, and then we'll go back to the main function. So we're gonna say let handles, and we're gonna go ahead and clarify that it's gonna be a vector of join handle, right? And this join handle is not gonna take in any arguments, so it'll be a blank unit type, parentheses here, equal vector empty. So we're gonna initialize an empty vector of handles, and for each one of these handle, we're gonna push it into the handle so that we can save all of the join handle into one, and then we'll loop over it later on and we'll unwrap it. So we'll say for handle in handles, and then we'll place that in there, right? Okay, so now let's go ahead and focus on this. All right, let's okay, so let's do a loop. We're gonna say for I in 0 to 3. So it's gonna be 4 loops. For each one of those loops, we're gonna create a new threads, right? So we're gonna take all of this and paste it in there. Okay, yeah. Okay, so now what we're gonna say is, for each one of those loops from 0 to 3, so 0, 1, 2, 3, that's 4 loops. We're gonna create 4 threads, and for each one of those threads, we want to write something. We want to write something to the data. So, and then after that, after we're done with that, we'll push it into the handles. So now the handles is gonna carry all of the join handle being sent back by the thread spawn, right? Okay. And then after that, we'll run over each one of the handles like we said, and then we'll join it. Okay, so now what's gonna happen is, for each one of those, we wanna add 10 to it, right? So that's gonna require a little bit of finesse here, because we're moving. So we need to go ahead and add, we're gonna do the data clone inside of the loop. So that for every loop, we have a new data clone, because the data clone is gonna be moved inside of the thread, so that we need a new one every single time we loop back from 0 to 1 to 2 to 3. So let's let handle equal thread spawn, okay, data, everything stays the same, okay, push, and for some reason, can I mutate? Oh, okay, so now that looks decent, right? So now we're gonna have 4 different threads. Each one of them is gonna push. Let's push I, right? Let's push I into it. So basically, whatever the thread is, writing data in thread I, and in thread I. We don't need to do this. Yeah, we don't need any of that. Okay, we're just gonna write the data into thread I. We're gonna add 0, 1, 2, 3 into this vector, and then at the end, we're gonna read it. Reading final data from main. So we're gonna read the data from at the very end to make sure we added the right values. And let's see the order of which it adds by the threads. Let's see. Okay, so as you can see, it added in the right order this time. It goes from 0, 1, 2, 3. So that's actually lucky. It doesn't. It's not guaranteed. I'm not sure why my computer is doing this, but see. So right here, as you can see, it's not guaranteed. Now it's kind of random, right? Now it's 0, 1, 3, 2. So as you can see, there's no guarantee of which orders that these threads gonna be ran. It's gonna be joined, pretty much. So with that being said, so the mutex is great, right? It solved our problem up until now. However, its limitation is that only one can lock it and then mutate the value and then unlock it at the same time. Now, what if we want to maximize that? Because what if we only want to write? What if we only want to mutate the data in one thread, and the remaining threads we just want to read it? We're not trying to write to it, so we don't want to have to lock it every single time. What if, is there a way that we can optimize this so that, yeah, if we need write access, you can go ahead and take your time with it, but if it's just read access, it should be shared, right? So there's a different data structure for that, and that's called RwLock. So that's read write lock. So it's basically the same concept as Mutex, except instead of lock, we use read or write as a method, right? So for this one, since I want to write to it, I'm going to use write. And at the end, since I want to read, I'm just going to say read, right? So that shit works the exact same. Nothing should have changed. Okay, as you can see, it works. Now let's test this theory that, oh, the RwLock will lock up the value only if it needs to write it. If it needs to read, it doesn't need to lock the value. Multiple threads can access it, because as you know, in Rust, we can only mutably borrow a value one time, and we can't have a mutable borrow and then everything else immutable afterwards. Like once you borrow, you can only have one borrow if you need to mutate the value. But you can immutably borrow a value as many times as you like, because technically you're not doing anything. All you're doing is reading it. So it doesn't matter if you have multiple threads borrowing at the same time. So let's see if this concept works. Let's say if we will only write to the data if the thread happens to be 3. Okay, so let's say we can do, let's see, handle, we can do this. If I equal 3, okay, and we'll do all that. Okay, I'll make sure I indent properly so that we know where the closure is, so that we know what values get moved into it. If not, then we're simply gonna actually no, we can just keep the same we can keep the thread the same, but let's say if I equal 3, okay, then we'll do all of this. Oops. Else we'll do something else, right? We'll do let data equal data clone dot read dot unwrap. Okay, so we're just reading. Print line reading data in thread I, and we'll list the data out here since we're reading it. Okay, and then we'll say finish reading, and then for this one we'll say finish writing here. Okay, so only if I is 3, so only the last thread should push 3 into the data, into the vector. Everyone else is just reading. So now in order for us to test this, let's say let's see here. Yeah, it's really hard to tell what's going on, so we're gonna go ahead and put a sleep we're gonna put a sleep method on so that we can really see what's going on here. Okay, let's do a sleep here. Sleep duration from seconds. Let's do 1, right? And then let's do reading. Let's do. So in order for me to prove that this works, right, I'm gonna say it's gonna take 3 seconds. Let's say reading the data is so much more computationally intensive than writing, which is not true most of the time. But let's say if it was, right, let's say this read data is gonna take 3 seconds to finish, whereas the write data is only gonna take 1 second to finish. What I wanna see is that the read data should start anyways, right away, all at the same time. You're gonna see reading data in thread, and then I'm gonna change this also to 0, just to prove that the write is gonna be by itself, right? So we're gonna see, we should see writing data in thread 0, right? Wait 1 second, and then it's gonna push, and then we should see reading data in thread 1, 2, 3, all at the same time. Like it should be able to start all at the same time, and then it's gonna take 3 seconds each. And then it's gonna be all finished at the same time. So let's try that out. As you can see, there you go. You saw how it took. So they started writing the data in thread 0 by itself, right? And then it finished writing. Now it's able to unlock the mutex again, pass it on. So the next 3 threads started at the same exact time, meaning that it was able to do that. It didn't need to lock or unlock. It just read the data, and then it took 3 seconds for it to read, and then everything was done at the same exact time. And then the final data in main has the 0 in it because the thread number 0 had wrote the index 0 into the vector. So as you can see, I mean, we'll try it again. Let's see here. We try it again. Boom. It started writing, it finished writing, then all 3 of the threads was able to read at the same time, or at least start reading at the same time, and then it finished reading after 3 seconds, and that was that. And then we return to the main function. We make sure that the vector has the 0 index that was pushed in by thread 0, and then we exit the scope, and everything is done. So as you can see, this is a very, very fundamental concept in Rust of how to use threads and how to use mutex, arc, and RwLock. It's pretty fascinating stuff. I really like it. For the next video, I think I'm gonna do channels. We'll show how to pass messages along in the channels. And yeah, so hope you guys enjoyed that video, and leave a like, thumbs up, subscribe, and I hope everybody have a great day.